busy spoiling myself.
Hey everyone, it's just a wake up right there. We got a lot of questions, it looks like, ready to go. Let's take a look right here. Can you do the chapter 17 homework starts with a researcher investigated the size? I can't find the p-value. Chapter 17, sports about baseball and football. Statue and project I'm doing intentionally. I'm confused how if I make up my company or use the Fortune 5. You can use whatever you want, Matthew. Any sort of company. Hey, amazing. Good to see you, Jesse, Jamarcus, and Sloan, and Matthew. So we got the size of the drinking cup one. Statue and project. It can be whatever company you want. Any company you want. Make up your own company. Sloan, great answers right there. The data shows the sugar in grams of cereal. Let's go ahead and do some questions here. It looks like chapter 17 is the way to go. Ask those questions about the project. I hate those. You ever get those calls? I had a call that just a second ago that I think might have been a scammer, and I used my name. I said, hello, this is, and I said my name. And it was like, man, I hate all these fake phone calls we get these days. People may be recording us or stuff like that. Of course, I'm recorded on the internet all the time. Oh, Mewbot. He's not awake. We got to wake up Mewbot. Thank you, Jesse, right there. Didn't realize Mewbot was not awake. Mewbot does not look to be awake. He is not awake. We didn't wake up Mewbot. Can we use the company that is given in the data? Come on, your own. You got to come up with your own. You got to imagine things. Whatever company you want is the company that you are creating for the project. It is your company. So as the prompt says, you will insert your name of the company that you're doing. All these points, and we cannot even get them. I know. I think, let me see if Mewbot's giving out points right here. So I'm doing the project on the donor data. On the document it says it's about PVA, the Veterinary Association, right? You make up whatever organization you want. So that is your goal, to come up with any organization you want. It is your company that people are donating to, your organization. So remember, it is your goal to come up with your context of the data. So that's the big thing right there, is you want to come up with what the data means, who the company is, what's going on. Core Plus Mathematics. Yeah. Let's go check out. I think these are all on the quiz, right? The first one we had was cup size, was it? The large or small cup. That's chapter 19. We're not doing chapter 19. We're doing chapter 17. A little more chill music. Let's get chapter 17 started right here. Okay. You are... I know, right there, right? I'll probably do a little bit of rounding at the end of the semester. Got a call from an 865 number, and I was like, I think this is someone who wants... I don't know. I'm trying to find a good apartment. Okay. Let's do that first problem right here. On the size of a cup. Okay. So here we go. Let's do it. So we are investigating if a size of a cup impacts how much liquid people put in the cup. Why is this a 2-sample T? So these are the important things we have to know when doing problems. Why is size of cup and how much liquid people put in it a 2-sample T? Why is it a 2-sample T? Great job, Jesse, right there. So why is this a 2-sample T? So we have to think about what is a 2-sample T. On the 1-sample T, I did where I put in my student ID. This is what I did on the first one. Yes, make sure it's the 200 plus the last two of your UTID for your sample size. That is correct. Wow, what... The total is supposed to be our student ID rates. Yes. Well, that is the sample size. Correct. The sample size is your student ID. Why is this a 2-sample T right here? So we have to know what we are doing. The 2-sample T. So with this, what does it mean for something to have 2 samples? 2 samples means there are what? 2 samples means there are what? Like when you say the 2-sample T, which is not a 2-sided test. It could be, but I think this one is a 2-sided test, but that's not what the 2-sample means. The 2-sample literally means, and if you look to it right here, there can be 2 means, and that, yep, Sloan, that is correct. there will be mean 1 and mean 2 created from sample 1 and sample 2 with standard deviation 1 and standard deviation 2. Now, the t part of it tells us what when we think about what it means for there to be a 2-sample t-test. So you could test like GPAs of men versus women. You could test freshmen versus sophomores on who can run faster. So the freshmen versus sophomores, the 2 samples, like you take a sample of freshmen, you take a sample of sophomores, and then, but it's not just the 2 standard deviations. Standard deviations are kind of part of it, but the t part of it, so great answers right here. The t part of it means what? The t part of it means what? Like the 2 samples means like freshmen versus sophomores. You're going to compare 2 groups. So that's what the 2 sample means. There's 2 groups, 2 samples. Mr. T is mean, so that's where we get the mean part of it if you're doing drugs. So this is where we have the mean part of it. So notice the color coding right here, 2 samples, and there's thus 2 means for each sample, and we're comparing the means. The t-test is where we use means. So when we do this right here, it really boils down to notation, only if you're doing drugs. Super nice guy otherwise. We love Mr. T. So the null hypothesis, a really great way to remember it, is that the null has the what sign. The null has the what sign. The null has the what sign. We're not going to click the button. We're going to remember that we're going to state the parameter of interest. The difference between the 2 means is equal, and the null has the equal sign. Great job, Jesse, right there. The null has the equal sign. We'll throw some more points in here. The null has the equal sign, and then the researcher's question determines what? The researcher's question, this is a great note to have, or write these notes down. The researcher's question will determine the what of the what. Because this is this. We're talking about over here, the researcher's question will determine the sign of the alternative. So they ask, did the glass size change? So if we say change, are we talking about increase, decrease, or different? So change is the word. Did the glass size change the portion size? So not equal, right? Is it different? So either it's the same, there is no difference, or the difference is not equal to 0 right here. And this is just the words of it. So when you think about how we write it out with words, we'll say they're the same or they're different. The mean for the smaller glass is the same as the mean for the larger glass. The mean for the smaller glass is different, as in their difference would not be equal to 0. Now, this is where we get to the end of our hacks method, where we have to find the p-value. So we can kind of take some guesses at this. If we know the t-statistic, we can probably get the p-value as a decent guess. But the t-statistic is going to be the formula. Let's write it down right here. You do get these formulas on the test. And the good news is if you know the notation, oh, thank you so much. Sloan, 1,000 points. Already putting the apps in the chat. We'll be going there in a moment. If you know the notation. Now, why does this not get a star? I'm going to remove that star later. Why is that not going to get a star? Like, what would the star indicate? And I think they're doing large, small minus large. Let me double check on the way it's done. Oh, where mu1 is the... Yes, okay, it is. Small glass is mu1. It's not a confidence roll. Yes, exactly. Great job, Sydney, right there. 1,000 points, Sydney. We're just going crazy on these points today. So the star is only used when it's relative to a level of confidence, and we use it for confidence rolls to indicate this is a T for a 95% confidence roll. So then you would pick the T based on the confidence level. This T is a whatted what? This T right here does not have a star. Really, it's like the first document I use is possessed. We'll change it here in a moment. This T, don't go big again, is a whatted what? Hey, Anson, good to see you here. This T statistic is actually, when you think about it mathematically, a difference. Great job, Sydney. Yep, it's a difference standardized. So it's a standardized difference right there. Because the difference is the top part of the equation. Like this right here literally is a difference between 2 values. And then the standard error down below is how we standardize that difference. It's very important that jump output shows you this. It's funny how I've knocked out chapter 17. I was watching... Yeah. Oh, the old applets. Yeah, they're good. And then Adam Spanbauer came up with the newer ones. So the old applets are good too, but the new one, what do you think, Sloan? Do you like the new one better? It's fine if you tell me you like the old one. That'd be interesting. Oh, exclamation mark T. Yep, there's the old T applet right there, which is really good. It's basically, here's the other T applet. It doesn't have the Welch's degrees of freedom on there. Well, Sloan knows the other commands right there. And here's our current one, which I should link. I should make it so I could link to the T, because if you click right here, I could update that right now, Sloan. Watch this. We're going to change something in MuBot's memory. So let me go to commands, and then we'll finish this question. So Sloan, guess what? After this, Sloan, try doing the T applet now. Do the T again right here. Yep. So Spanbauer made these. Shout outs to Adam Spanbauer. And now, if you look, MuBot has updated his mind right there. He now puts you to the Adam Spanbauer one. So what's really good is a lot of people, and let me do this. Let me go to the chi-squared just really quickly, because I think chi is also a command. You can try chi. And let me update that one. You might do it before I do it, but chi is also a command that you can do. And it is now updated. Okay. So now I can send people to the chi-squared applet too. Okay, awesome. Yep, thank you. Answer right there. So now that is going to go to the Adam Spanbauer one. Would Y bar 1 be the smaller glass? That is correct. Great job right there. Going back to the problem, it does indicate that mu1 is the smaller glass, so Y bar 1 is also the smaller glass. So do know in your notation, this is noted as 1, this is 2, and 1 and 2. By the way, the problem has dictated that mu1 is the smaller glass, so Y bar 1 is the smaller glass. Excellent work. So really, at this point, we're just solving a math problem here. We're just solving for the t-statistic with the computer that doesn't want to work with us. Come on, computer. When I went to a new sheet yesterday, it worked fine, so we'll pretend that it's not having issues here. We're just going to plug in all the values. And so we go right here. We do the means. So 5.38. The t-statistic, will the t-statistic be negative or positive? Will the t-statistic be negative or positive? It's a negative difference. So the t-statistic is, I love this computer. T-statistics, definitely great job right there, going to be negative. So there we go. And let's start solving. We'll solve the standard error first. Make sure to do 1 point. This is usually where you'll make errors. 1.72, square it, divide by 22. That's the first standard error. Now we want to add together both of them to get a combined value. Divide by 23, and there we go. Is that? I think, yes, everything looks right. Add them together and square root. Do not forget the square root. 0.673. Now, don't put the number, like, don't just divide by that. Carry all your decimals by using your copy option right here, and then subtract 5.38 minus 6.67. And there's the difference, 1.29. The t-statistic looks to be a little bit smaller than 2, which is going to be interesting right here, because we can probably take a guess at the p-value. So there it is, 1.914. And then that's what Sloan gets. Double check your work, Jesse, and let me give some points out here for everyone helping out. So 1.915 rounded. 3 decimals is usually fine for these. Don't round till your final answer. And let's throw some points for people helping me check my work. Jesse, if you can confirm this, that Sloan and I got the same thing. If you can confirm the same answer, that'd be awesome. But that looks to be the right answer. And then remember, don't use this number here, because if you don't carry enough decimals, you might get slightly different answers. That's why that is slightly different, and I would carry all the decimals till the end. So with this, here's the thing. We don't have everything we need right now to get the p-value. We'll worry about that here in a moment. The degrees of freedom are probably close to about 40, which means I got a different answer for the bottom part. You did? Oh, let me double check that. 1.72 squared divided by 22. That 2.71 squared divided by 23 plus square root. Standard deviation. Oh my gosh. We got to throw Jesse 5,000 points. I think that's it. Yep, Jesse saw it. 1 second, Jesse. I think Jesse's now done it correctly. Jesse, what's your standard error on the bottom? Wow. It's so easy. That's why I've gotten out of practice, because I'll go over to R and just put the values in and let R solve it for me. And so that's where I make errors, is because I'm like, well, I could just type this into R. 8.4 is the bottom now, which is going to change it. What you doing, computer? Thank you, Jesse. I think Jesse got it. Yep. Jesse, we got to throw you some big points for that right there. And Jesse said it's 885 or 886. 886. There we go right there. And now we take 1.929 negative, divide by, and there it is. Great job, Jesse. 35,000 points. Really appreciate these catches right here because, and we'll do that one here soon, Savannah. Thank you so much. Really good catch right there. And now we draw the curve. So now, does anyone know the p-value should be a little bit larger than what? So the p-value should be a little bit larger than what? And here's the hint. We landed here-ish at negative 1.886. That's where the t is at. We're doing the does not equals test, so we have to take this area right here and reflect it to the other side. Yeah, so wait, I think, Jesse, you're on the right track with that. Look at what our line is close to. What do you notice our line is kind of close to? And this is a t with about 40-ish degrees of freedom. We'll find the degrees of freedom here in a moment. 0.06 is the next number I'm going to guess. 0.072. That's my guess. That is a guess. It's going to be within about 1 or 2% of the answer. So we're going to put these numbers in, then we're going to check. I like to do this to show that we don't always need to use the applets. Round to 3 decimals. So this is going to round up right there. There's the 3 decimals. Now we need 4 decimals. I got this a day or two ago. If I get this right now, that is insane. But very clearly, we need to what the null hypothesis here. I will promise you that it is above 0.05. So very clearly, we are going to what the null hypothesis. I will promise you that the p-value is above 0.05. I know that for certain. So we are definitely going to what the null hypothesis. We are definitely going to what the null hypothesis. We're going to fail to reject. Great job, Jackson, right there. We're going to do not reject. There is not evidence for the alternative. Does not provide evidence that there is a difference. And I want to point out when you're doing this, I think I still have, do I have the document up? Let me see if I do have it, because we wrote everything out. And you want to be able to interpret these results. Here it is. Good deal. My p-value of 0.07 is greater than my alpha level of 0.05. This means I do not reject my null, that there is not a difference. I do not have evidence for a difference. And make sure to check your alpha level right here. And here's the big thing. How do we get the p-value? So put it in the chat one more time. Let's get the actual p-value now, because this is usually where people get stuck. So where are we going to have to go? And good to see you here, Martin. So Sydney's got the apps, and better yet, and thank you, Sydney, right there. Let's start Sydney at 1,000 points. Now we have a link specifically, and thank you, Sloan, for helping out with this. We have a link specifically to the T. So now if you look at the T link right there, Jesse's posting again. Thank you, Jesse, right there. The T link that Jesse's posting right there is going to bring you right to the T distribution. Yeah, drop the questions in about the project. And so now this brings you right to the T right here. Now, every T has with it what's. Every T has with it what's. Every single T will always have with it what's, because we have to know which T we're using. So every T will have with it what's. I've got it kind of right there, degrees of freedom. That tells you the shape of the T. Now, the degrees of freedom for a one sample T are n-1. That's how you mathematically find them. The degrees of freedom for the two sample T is a too complicated formula that we're not going to solve right now by ourselves. We're going to use the applet. So now we go over here, and here's the information with the sample size, 22 and 23. So 22, 23. And then we have the standard deviations, 1.72 and 2.77. So 1.72 and 2.77. I said about 40. It's actually 37.01. And now we go back and we go to find the p-value using the T. Make sure to just put in your information with standard deviations. Great job, Jesse. Thank you so much. Becoming a pro at these. And we drop it right here, and then we input our T. Now, when you input the T, you have to think, am I doing a what test, or a what test? So I'm going to input the T just for safekeeping right here. But what's the difference between these buttons right here? So if you look at these buttons, I need clarification. Oh, yeah. Yep. Oh, that's a really good. I'll make a video. Let me do that next here, Martin, because that is a really good question. So this is the between for the does not equals. This is the below for the less than alternative. This is the greater than. And when do we use outside? Or wait, whoops. Not, we don't want to use between. We want to use outside, which is this. When do we generally use between? Between is generally used when we're making what's. Between is when we're going to generally be making what's. That might be it. Great job, Jesse. I was kind of close, not close enough, it looks like. Should went with the 6 right there. Between is for confidence intervals. So when you're doing exactly, Jackson, great job right there. So you can see the differences right there on the buttons you click. And we usually don't find a p-value. We usually say, like, if you make a confidence interval, you go right here and say, find the t using a p-value. You'd go between and enter this in. So what's really interesting, Jesse, watch this. I'm going to reverse engineer. Jesse told me what the p-value is. And so I can confirm the answer Jesse gave in a reverse fashion by finding the t statistic that we found. Now, this is not how you should solve it. How you should solve it is find the p-value using the t you just got. We're going to find the p-value we want to find using the t we just got. So we're going to go to the outside right here, put in the t statistic. That's not the t. There's the t statistic, and then there's the positive version, and Jesse has the p-value right there, and we round it to 4 decimals up here, rounded to 4 decimals. Between is because of confidence interval. Exactly. Between is contained in. Oh, nice. Jackson. Let me throw Jackson another 1,000 points. Those are some really great answers. So I don't think I was close enough in my answer right there. Everything should be correct. 4 decimals, 3 decimals. I think we've done it. We've done it. I was a little bit worried when you hit that submit, as though I misread something. And good way to put it, Jackson. 1,000 points. Excellent job right there. I'm going to do a quick section about some weirdness you could get, and then why. I'm lost on p-value. Which part are you wondering about, Jamarcus? So you have to go to the t-applet, and then you have to have your t statistic. So to get the p-value, go to the t-applet. Will a chart like that be on the exam? We won't have any charts, but you'd have to know what is presented to you right here. And the best way to know what the exam looks like is the Canvas content. So if you're wondering what will exam questions look like, Canvas content is the best way to know. You might get jump output on the exam. Canvas content shows jump output. And I'll show some jump output too. We've done a few other problems with jump output. So make sure to put in the positive and negative version of your t and do the outside, because this is a what test. And then we always want to confirm, does my picture over there on the left look something like the picture there? Did the picture I drew look something? Corpus mathematics? I think we'll do that next after the question on the project. So you always want to draw your own picture. Try to draw your own picture. I promise it's worth it to be like, how should this look? I'm doing the does not equals test. So I want to shade the outside regions. I'm going to shade below the t and outside the positive version. Nay, Jackson, that's great to hear. Yeah, it makes things really easy. Like that, if you know how to use it, you're just like, oh, let me run this test. Done. I mean, that's how a lot of statistics is done. We don't usually solve stuff by hand, but you have to know what is going on. You have to know what jump is showing to you, what it means. Like if you look at jump output and you know what it means, then it's just pointless. Yeah, let's do another question right here. Let's talk about the project. So we're going to look at some jump data right here. I'm going to show you some confidence interval stuff. So if you want to learn more about confidence intervals, this is a great review. And I'm going to talk about some weirdness right here, like when your confidence interval doesn't match your test. So let's bring up some diamond data right here. And let's talk about project when the confidence interval doesn't match the test. Stat tool 1, project help, when the confidence interval. Okay. So this is a little bit more high level. I like Sloan right there. Chapter 19 is so quick if you got jump. So this is a little higher level ideas that I want to present to you, but it's going to help with understanding why you might see some weirdness. So first off, we often use confidence intervals to see if values are possible. A confidence interval will tell us that a value seems possible when that value is where. Yeah, no worries, Martin. I hope this will clarify everything. A confidence interval tells us that a value is possible or believable when the value is where. There's so many cool things it can do. This is high-level software. Companies like Eastman use it. A lot of companies use jump. When does a confidence interval tell you a value is possible? If I ask about the carat of a diamond, the average carat of a diamond, and I go and look at that, and I go right here, and I look at the confidence interval, and I see that the average price of or average carat of a diamond is somewhere between about 0.8 to 0.83 or so. 0.78, excuse me, to 0.83. I said the mean first. So the values contained within the confidence interval are plausible values. Now I want to point to what you should theoretically think. Now, if I enter, let's say I were to run a test, and I were to test exactly this value. Does everyone see that 0.8382828? What if I told you I could tell you the p-value down to the millionth decimal place? So I am testing a value at the very end of the confidence interval. And I'm going to say to you that I can tell you the p-value down to the thousandth decimal place. You believe me? Well, and I bet you can too. For 5,000 points, since this is on the edge of believability on a 95% confidence interval, what would be the p-value on the two-tailed test? Remember, this is on the edge of believability on a 95% confidence interval. That is the very extreme thing we would believe. You're like, well, it's barely inside the interval, so I'd just barely not reject it. That's the hint. I would just barely not reject it. Think about when we reject and how you could be like, well, then the p-value should be exactly this for the two-tailed test. So it's on the barely edge of believable. That's on the very most extreme edge of, I guess I'd kind of believe it. I mean, but I'm really close to rejecting it. I mean, I'm just as close as rejecting it as you could be. So for 5,000 points, big question, theory question here. Because if you get this, you totally understand what's going on right here. That value is on the edge of believability on a 95% confidence interval. That's the hint. So the two-tailed test p-value should be what? Because we can barely not reject it. This is a big concept. Think about alpha and when we reject when p-values are less than alpha. So the two-tailed test p-value would be what? So Jesse, I think you're on the right track, and Jackson's on the right track too. Take your answers and combine them. Remember, we reject when p-value is less than alpha. Remember, though, alpha is not 0.5, though. The assumed alpha, unless otherwise stated, which a 95% confidence interval directly matches to for the two-tailed test. We don't reject at 0.05. We reject when it's less than 0.05. So the p-value on the two-tailed test will be exactly 0.05 because it's on the exact edge of what is believable. Jump probably shouldn't put a star on that. Maybe I didn't carry enough decimals. I wish it didn't because we reject when p-values are less than 0.05. P-value of, well, so we could get that if we put something that's just barely where. How could we get that? We could put something that is barely where. Now look at this value. That value is just barely where. So I think that's going to be about the p-value we're going to get, Jesse, because that is just barely where. That value is just barely outside, so you just barely reject. Does that make sense? Who thinks? I hope this brings in some clarity that this value that's just barely outside the interval, as Jackson's saying right there, great job, Jackson, is a value we just barely reject on the two-tailed test. This one that's on the perfect edge of the interval is one we technically do not reject because it's on the edge of what's believable. So we would have to fail to reject because p-value is not lower than alpha. Jump, you should not put a star on that. So with this right here, this coincides perfectly. So Martin's probably wondering, what in the world? So we are using, and here's the catch, we are doing a t-test with a what interval. For 1,000 points, we are doing a t-test with a what interval. It's a very technical idea, and so I wanted to teach some of the basics here. We are doing a t-test with a what kind of interval? We are doing a t-test with a what kind of interval? So this is a t-test that coincides with the what kind of interval? What would we call the interval? It's an interval to figure out the true mean. So that's a t-test from it is a confidence interval, and it's a t-interval. So that, and good guesses right there, that is a t-interval that coincides with the t-test. So that's the thing that is a little more advanced that I want you to see right there. So the t-interval comes to the exact same conclusions as the t-test. Now let's head over here and see something weird. I'm going to now show the issue I've gotten, and please email me if you see anything weird. I'm going to subset first just so I can have two groups like you do. So I'm just creating a subset of the data to where I only have 2 groups of data. You don't have to do this on the project because you'll already have things with 2 levels. That's a 2-level categorical variable now. And I'm going to analyze the distribution. I'm going to go over here to the cut of the diamond. And we're going to take a look at the cut of the diamond. And we see the 2 groups. And now what I'm going to do is I'm going to make some 95% conf rolls like you have done right here. There's 95% conf rolls. And now I'm going to choose a value on the edge of believability like we just did. And theoretically speaking, just going with your previous knowledge, and I think we're going to see a problem right here. I'll explain why. If I pick these values that are on the edge of believability, which is not what you do on your project. This is not how the project is done. Theoretically, what are you thinking if that's on the edge of believability of a 95% conf roll? What theoretically do you think the p-value should be? And I'll explain the problem here because this is what don't worry, please ask questions like this. So since that's on the edge of believability, theoretically, what would you think the p-value would be? Remember, edge of believability. Same sort of thing we just did a moment ago. It's on the edge of like, well, I can barely just not reject that. You would barely not reject that. With a 95% conf roll, you should barely not reject that. Like, just as close as we can get to not rejecting it. And we're doing the exact same concept we just did a second ago over here, where we just barely did not reject something. So remember, on the edge of believability, we just barely not reject. So theoretically speaking, if this value here, don't put those values in for yours. We're not doing the project. We should get 0.05, right? I'll show you why we don't, because we shouldn't now. Now, if you notice how the Pearson came out to exactly 0.05, well, it actually confirmed what we got. So I'm shocked we do get the same value. And that's good. We got the theoretical answer. The Pearson is what we use. But here's the problem. The problem is as follows. This test right here is done using the chi-squared. Now, we haven't actually done this test in class. It's not a proportions test like we traditionally do. Different statisticians have come up with different ways of doing it. And this says computed using score confidence intervals. So this is using the chi-squared to do the test. And this is using score, which I don't even really do. We generally do these with z's, and we do these with z's. So if you were to use the same methodology, you would come to the same conclusion. But if you're not using the same methodology right here, you might not come to the same conclusion because it's a different statistical method which doesn't align perfectly. So that's why I was illustrating with the previous example. We came to the same conclusion over here because our t interval was then we could use it to do a what? Our t interval could be then used to do an analogous what? Our t interval could be used to do a what? And I'll show one last thing here too. The t interval could be used to do the t-test. So it's the same sort of metric. The last thing to mention on this, and we are talking a good bit of theory right here, is when you do a confidence interval, the t interval uses y bar plus or minus t n minus 1 degrees of freedom star s over square root of n, and the t-test uses y bar minus mu naught over s over square root of n. Now, the proportion interval uses p hat plus or minus z star p hat times q hat over n, and then square root. And then the test uses p hat minus p naught over, and here's the thing, p naught q naught over n, square root. So what do you notice? And this is why you might come to different conclusion on this one too. What do you notice? The way in which a proportions test is done, and this is equal to the t with degrees of freedom n minus 1, and this is equal to the z. Well, they are standardized, But the test, the proportion test, core plus mathematics. Yep, we'll do that next, Matthew. You got it. Or Matt, sorry, Matt. The t uses the same standard error, where the proportions uses the standard error over here. This is the standard error of y bar. This is the standard error of y bar, just the concept I've circled. This is the standard error of p hat because it comes from a sample. And then this one over here is the standard deviation of p hat because it comes from the truth or an assumed truth. So that right there is a very small difference, which then creates differences in the calculations of how it's done. So this is more in depth. If you use the same method where you use the t with the same methodology, you will get the same result every time. You will get congruent results on something being in an interval and rejecting it, or being out of interval, rejecting it, or not rejecting it. And if you were to have things like this down here, where you don't have the same congruent method, then you will not receive always the same exact result. It'll be similar, and you can just you can do the tests and stuff like that. I use confidence intervals for tests all the time. It's the easiest way to look to see if a value is plausible, but then you could run it using the test if you want to double check. But usually you want a really small p-value. So if something's way outside the interval, you would definitely reject it. Jackson, does that help right there? This has been a little more in-depth, a little more mathematical on why tests sometimes don't line up. Sometimes you use a different method, like a score method versus a chi-squared. Sometimes the calculation done for the standard deviation of the standard error is different, and those differences in formulas will create differences in calculations. So that's a pretty in-depth example, but I've gotten a few emails about that. And the biggest thing is, so the moral of the story is, to see if a value is plausible, a lot of times we can usually just don't worry too much if it's different. Well, P naught is the hypothesized truth, and P hat is what we saw. So remember, P hat is the sample proportion, and then P naught is the hypothesize. So probably, especially with the project, the easiest way to do the project, and the graders should honor this, the easiest way to do the project is this. Do I see 50% in this interval? Question 8 from, Matt, I think we'll have time for that. We're going to do core plus mathematics next. Do I see 50% in that interval right there? Do I see 50%? No. So very clearly, using the confidence interval as a method of rejecting or not rejecting, I can 50%? Using the confidence interval as a method of rejecting, I can reject 50% or not reject. Because I look at my interval right here, lower, upper. I am 95% confident the true proportion of ideal diamonds. I can reject it. I do not believe 50% is the true proportion of ideal diamonds, because 50% is not contained in the interval. I would reject it. And so if we tested 50%, we should come to the same conclusion. If you do get incongruent results, don't worry about it too much, because the mathematics we just went through kind of explains it. Let's do that core plus mathematics question right here. We got the core plus mathematics. Two teaching methods. Core plus mathematics. Great work. These are tougher chapters. That's why we go a little bit slower. In our class, we've been having a review day, and where we've just been doing assignments, which is today for chi-squared. And then we've been having a day where we go over the theory. So you want to attend theory days. See, in this semester, I don't know why I'm saying this. You want to attend the theory day, and then you want to attend the review day to practice it. So you learn something, then you practice it. That's how we do. Okay, Stat 201, Chapter 17 quiz, core plus mathematics. Okay, the core plus mathematics. Let's take a look at it. Here it is. First thing we see is what? Chapter 17 sports bar? Yeah. Let's do that one next. We haven't done it lately. There's two. Yeah, let's do both. We'll do both, and then we'll do Jesse's question. Yeah, I'd go with that, Martin. It's the easiest way to explain it. And then the test is not super required. It's just a good thing to understand. And it most of the time be congruent. Well, we'll take a look at that, Jackson. I think we're pretty low. Maybe we're lucky for above 50%. I don't know. Tell everyone do the TN voice. So what's the first thing we see right here? And we should know what it means. You should be able to explain to me every one of those values. I know, right, Jackson? We'll tell people to do it today. I get those bonus points. I'll send out email reminders too. I sent out one last night. Was it just normal TN voice? What do we see right here to start? What do we got? What is this? What is this? What's that? What's all this? No. Yeah, you should be fine. If you think the graders are not fair, let me know. I've regraded. The graders work super hard, but I always get the final call on things. We see two means. We see
Notation, brother.
We see notation. So what does this tell you? Like if you had to write a sentence about this, if your whole final grade was write one sentence explaining that value. So the CPMP is like a method students learn it. What does that mean? What does 320 mean? So these are like ways students learn mathematics. Yep. And so I would say there were 320 students who did the Chlor Plus mathematics program for learning mathematics. The average score they got on the exam was 57.36. The variation in their score was 32.08, measured by the standard deviation. Everything else could be said for the below data. And so why are we doing a two-sample T? Because we have what's, and we're comparing their what's. We always want to know why we're doing the two-sample T. So we're doing the two-sample T because we have what? We are comparing the means of two groups. Does that make sense? Two samples comparing two means. Exactly. And Jackson, great job. We're throwing 1,000 points for everyone, all these comments, because we have a categorical X. I think a lot of people forget to realize that if you have two groups, that's two categories. And a lot of times people think, oh, wait a minute, that doesn't mean it's quantitative. The important thing, as Jackson illustrates, is that you're comparing a Y, which is quantitative, so you would generally get something like this over here. And I do want to point out, as we keep doing these questions, you should know what the jump output looks like, and we can very quickly show one by going to analyze fit Y by X, go here, and this is not part of the question, but we should know how to analyze this output and look at it for the two-sample T, excuse me. There is a very statistically significant difference between the carats of an ideal diamond versus a premium, where premium was seen to have about 0.16 more carats, and we're 95% confident the difference is somewhere between this, T statistic, different standardized, and p-values. So know how to look at that output that is on some of the Canvas content, which we did yesterday. You could see that output on the test, some of the Canvas content, and we're kind of doing this work here by hand, and we see side-by-side box plots, just so you can see we can get the side-by-side box plots if we go over here to quantiles, and there's the side-by-side box plots with the box plot information, which we could also do on the project. Okay, so with this, we now need to run the test. Knowing nothing, I have method 1 and method 2. If you didn't know anything about these methods, what would you assume the scores are on these methods? If you didn't know anything, like a starting out belief without evidence, what would you assume? Yeah, Jackson, we've got the whole, I'll post it here in a second. We've got a whole video going over step-by-step kind of each thing. Thank you, Jackson, for asking. We'll post it here right after this one. What would you assume about these methods? Like student uses method 1, student uses method 2. Well, they might want to show that. They might want to show that the Core Plus... Well, so before we did this, and Jackson, good answers right there. Before we do anything, what might we assume? Before we collect data. Without data, what might you assume? You don't have any data now. You got no data. What would be your initial null starting assumption without any data? So you don't have any data right now. I took away your data. We're at the ground zero. We just started. No data. So what would you do? What would you assume? Well, when we don't know anything, we would probably assume that the two methods are about the same till we have evidence otherwise, right? So think about what I'm writing here. That the true average score is what? What does this say as a sentence? Like if we had to read that as a sentence, and we could write it that way too. So that's another way of writing it, that if we write right here, the null states that if you took, we'll put C minus T is going to be that. This is the same. And so Jackson has it right there. The test scores are equal. i.e. their difference is 0. Look at Jackson. We got to throw Jackson 1,000 points. Think about what Jackson just wrote right there, because we just wrote that out as a sentence. Sloan, also another 1,000. Thank you so much for the video link right there. Jackson said that the two test scores are equal, i.e. their difference is equal to 0. The true mean of the test, that if students were to do this and use either method, there would be no difference. First thing we highlight right there, or that their difference is equal to 0, or they would be equals, the first thing. So the alternative, and you don't have to write it both ways if you're trying to write this out, is that the core plus mathematics is, well, let's see if they're doing not equal to. How should we figure out the alternative to this? How should we figure out the alternative? I don't know if it's not equals. To figure out the alternative, we should do what? So, what word problem? Let's see. We look to, is it not equals? We look to the researcher's question. Researchers compared with those taught. I do not see. Does anyone see any sign of direction on this? Is an innovative approach to teaching mathematics that engages students in groups and investigates mathematics after field teaching over a 3-year period. Researchers compared the performances in one study. Students had to solve the word problems. What do you conclude? Okay. So unless there is some sort of indication of direction, which they might want to be showing it's better, we should assume the does not equals alternative. Now, I wish I had flashing alarms on this. We should assume two-tailed unless otherwise stated, but be careful. There's a small chance they might want to be showing that the core plus mathematics is better. It should be more clear. It should say, is there evidence the core plus mathematics is helping students? That is what we talk about when we talk about alternatives. Is there evidence? So the sign of the alternative right here is based on the researcher's question, and we do not see evidence of a direction, so I'm going to go with does not equals. We're jumping right to the t statistic right here. And so for the t statistic, we have to go and solve the data. So it's very important which way we subtract the means. Do they indicate which mean is... Oh, here we go. Mean 1 is core plus mathematics. Mean 2 is the traditional. Does everyone notice that? The way they've done their notation is core plus mathematics is mean 1. Traditional is mean 2 because it goes mean 1 minus mean 2. So make sure to know that. And you could put little ones right here, indicating to you this is 1 and this is 2, i.e. sample size 1, sample size 2, mean 1, mean 2, standard deviation 1, standard deviation 2. Man Moose New City. Yeah, we might have time to Marcus. That we've done that one in other videos. I can find it for you here. So I'm going to try to do as many new things as we can. We might loop back to the Man Moose New City, but we do have a video on that, so I can send that out. And the degrees of freedom are given. It was like basically 600, right? It was like 590-ish. At this point, the decimals are not going to make that big of a difference, but that is notation we need. Great job, Jackson, right there. So now we do y bar 1 minus y bar 2 over... Oh, thank you, Jackson. And 0.69. At that point, the degrees of freedom are not going to be a big deal, or the small decimals. And standard deviation 1 squared plus standard deviation 2 squared over sample size 1 over sample size 2. Equals t with the degrees of freedom given. So that's what we're talking about right there. And now we go and start plugging in numbers right here. And so the mean is 57.36, 5388. And then the standard deviations are 32.08, 320. 28.47 over 273. And now we find and we solve. Hey, Courtney, good to see you here. Let's see if we can solve this out. 32.08 squared divided by 320. There's the one standard error right there. 28.47. I guess it's not quite the standard error, but similar. There's that. And the standard error of the difference is 2.48 right there. We are working on the Core Plus Mathematics Chapter 17 problem. We might try to do the other one too. Remember, carry all your decimals till the very end. We're going to save this number right here and then do 57.36 minus 53.88, 3.48. Then we're going to take that 3.48 we got right there and divide it by the longer version of the number and get the t of 1.4, 1.3992. That's a tougher one to guess. So before we go, this is on the quiz. Good question. This is the quiz question. So what does Brian always do before he goes over to the applet? Before we go over to the T right here, which you can do that right now if you like, but I highly suggest doing what? I highly suggest doing what? Before going to the T, always try and see if you can do this. Guess it. Oh, I like that, Jackson. Yeah, guess it, draw it out. See if you can take a guess at it. So we like to take a guess because it shows we understand what the T is finding. So if we draw it out, 1,000 points, Jackson right there, we're going crazy on the points. If we draw it out and take guesses at it, then we understand what the applet is doing in the background. The applet's going to give a more exact answer than our guess. So we landed at the T of, that's where our T is at, 1.4, which is about here-ish. That's our T, and this is a T just as extreme. So the p-value is equal to this. So anyone got a guess at it? Someone's probably going to look it up and get the exact value. The p-value has to be somewhere between, I know for certain, it's between 10.10 and 0.20. It's a tough one. It's a very tough one. Between 0.10 and 0.20, it's probably about 0.143. That's a guess. So that is, ooh, Jackson. If Jackson got a better, good guess, Jackson. I'm going to throw 5,000 points if you, I'm just throwing 1,000 right now. Jackson, 5,000 points if you beat my guess. Let's see. So the degrees of freedom were 590. The question gave it 0.069. If you got exactly it, I'm going to wonder. Now we put right here the minus version of it, and we put right here the plus. And what was my guess again? I think we were both really close. Oh, man, Jackson, you were closer. Jackson said 15.5. I said 14.3. Jackson earning everyone 5,000 points right there with that amazing guess. Jackson, when people say, Brian, how do you do it? You can tell people, I make better guesses than Brian at these. So yeah, Jackson, I mean, for all intents, you were less than 1% away from the actual value. And all you did was just kind of look at this and say, it's about 15%. And that's what I'm like, the applets are great, but think about this. I always point this out here. I've got this drawing over here on the side of what I think it'll look like. And so if you look at the drawing, you're like, well, yeah, Brian, your drawing kind of looks like that over there. So that's what we try to do is we try to take a good educated guess at it and try to have an understanding. So great work, Jackson, right there. Looks similar, and that's what we go for every time. There's where our T is. There's the reflection on the other side. So that's where I mark the T over here, reflection on the other side, and p-value to 4 decimals. Jackson was kind of close enough. Let's find that next right here. It's the man moves to a new city question. So we have the T, p-value to 3 decimals. We'll just delete that one. The T statistic to 2 decimals is 1.40, I think, rounded up. And state your conclusion. This p-value is very high. So what would you conclude right here? So this p-value is very high. It's very much higher than the null. Remember, we go to our phrases right here. My p-value of 0.162 is greater than my alpha level of 0.05. This means I do not reject my null hypothesis that there is no difference. I do not have evidence for my alternative that there is a difference. Practice writing that out. So we fail to reject the null. There is not sufficient evidence. Oh, look at this. Oh my gosh, that's so good at the end. Right here, we have just confirmed the what with this. And I think we're going to do Jesse's question next. Thank you, Jesse, so much for waiting this whole time. And we're going to we'll find Jamarcus a video on that. What have we just confirmed right here? What have we just confirmed? We just confirmed the two-tailed. Exactly. Towards the end, we finally confirmed. And did we get it right? We did. Great work. We're on a streak. I don't think we got anything. We almost had one error this morning. We don't like errors, but Jesse caught that the standard error was miscalculated because I wrote a 7 that looked like a 1. So great job, Jesse, right there. And we did confirm that it's a two-tailed test because we're looking for evidence of a difference. Evidence of a difference would indicate the does not equals. So very good confirmation down here at the end. Let's do the sports reporter. And 2 seconds later, I'm going to find Jamarcus that video. Thank you, Jamarcus, for waiting. We haven't done the sports reporter this semester. So that's why I always try to do new things. And if we haven't done something this semester, that is going to be what we do. And thank you so much, everyone who finds videos. You're always welcome to do that. New city. Here we go. I think March 2nd might have done it. November 11th. Man moves to a new city. Bike routes, new city. November 11th here. Oh my gosh. I'm looking rough in this video. Gosh, what is... Like a... Okay, I don't look at... Just like head on, my hair's all crazy. Oh, what's going on? Copy video. I think, did we do it during class? Did we do it during class? We might have done it during class. Yeah, search is a great option right there. I think it's fun to point that out. So if you want another version of it, you can go with long hair Brian right here working the problem. So there's... And... Oh, this is New York City data, chapter 7. So... What do I look like? Perfect. We'll just keep craziness. Okay. It's weird seeing all these videos yourself. So we are doing the sports one, right? Sports. Here's the core plus mathematics on the other one. Margin of error would be about half the length of the interval. Four decimal places. Holy mackerel. 99% confidence, the error would be larger because the value increases. 95 with a 9% comfortable. The average of students taught using the CPMC using the higher than the traditional because it's CPMC minus. Does this result suggest we'll have significantly? Yes, because 0 is not in the interval, only positive values. That should be right. There we go. Let's do the other one right here. So kind of a speed run of that question, just looking at the interval because it's completely positive. So the first mean, there's evidence the first mean is higher, and 99% confident would be 99% confident would be a wider interval, and the margin of error is half the length of the interval. So I mean, it should be just 6 to 12. If the interval, last question here before we do Jesse's question, if the interval right there was 6 to 12, what would be the margin of error? If the interval was 6 to 12, which it's not, what would be the margin of error? If it was 6 to 12, it'd be 3. And then what would be the center of the interval, which is kind of close-ish to these numbers? It'd be, 3.0. 6 to 12 would be plus or minus 3 from the center of what? 9. And there you go, Jackson. So that's the important things to realize. It's just harder because of the decimals. Carry your decimals half the length of the interval. Yep, Savannah, good work right there. Thank you. I think you had asked. I wanted to kind of speed run a little bit. 99% is always going to be wider because the value we use for like Z or T gets bigger. That controls the percent confidence. And then down here, we're talking about averages. Since the interval is positive, there's evidence that the first mean is higher because it's first number minus second number means positive interval, first number is higher, and the interval does not contain 0, so we do think there's a difference, i.e. we basically did a hypothesis test. Sports reporter question time. Sports reporter. We'll speed run of a question. Where's the sports reporter question? Sports reporter. I really appreciate everyone being here. We're doing a lot of questions today. And just being here interacting is the number one way to learn. We're watching these videos in the future. A lot of people watch them in the future, but watching live is the way to go. Here we go. Chapter 17 quiz. Sports reporter. A sports reporter. Okay, here we go with the sports reporter. Let's talk about how to do it. First thing we see is what? Boom. What do we see first? First thing we see is what? Let's go grab it. What do we see here first? What do we got? What is this? What are those? I agree, Jackson. Yep. That's what I like, and I try to reply to everything I can. Oh, thank you, Hayden. A lot of people like this shirt. I appreciate that, Hayden. It's a classic shirt. I think my roommate got it for me. It's like, I don't have many like light purple shirts. I don't know what this color even is. It's like a magenta or something. And it's Dig Dug. Dig Dug's awesome. It's like, my skin tone is like, this is one of my favorite shirts. I've had it for, gosh, 13 years. What do we have right here? What is this? What is this? This is notation.
Notation, brother.
Notation right there. 2 samples, 2 means, 2 standard deviations. We got to throw 1,000 points right there for that. Got 2 samples, 2 means. We got notation. We got that we talked to 27 football players. Their average age, or 27 baseball players, their average age was 27.3. The variation in the data, so it probably looks something like this. We'll pretend it's normal, nearly normal. Condition number 3 for 2 means. It would probably look something like this right here. And the center of it is about 27.3, and that's from 27 observations. And then this data would look something like this right here. And why am I drawing it? It's going to be at 25.12. Why did I draw it a little more like this and not as much like this? Because if you look at it, the data for football players actually has a what or what. So why look at the area I'm pointing out right there, and I'm kind of to illustrate what these things mean to me and how I understand the data. So the reason I would draw it like that, just as an idea, smaller spread, Jackson, perfect. Yeah. So that's why I'm illustrating the center right here. Remember, shape, center, spread. I don't technically know the shape of it, but I know the centers. I know the spread with metrics of mean and standard deviation. And then once again, we always point out, and I'll say it this time, we're doing the 2 sample right here. So here's 2 samples. And then by comparing 2 values or 2 means, we're doing the t. So the 2 sample t compares 2 means. 2 samples, 2 groups, baseball, football players. So we'll get sample size 1 and sample size 2. We'll see if we're subtracting it this way right here, which is very important to how we work each question. It says right here, assume that mean 1 is baseball, so we can do it in this order. So saying it as a sentence, we're saying that the difference between the means, if our null hypothesis, which this one's correct, is that the difference between the means is what? Like if you read here, my null hypothesis, here it is, my initial belief is that the mean for the mean age of baseball players minus the mean age for football players is equal to 0. Great job, Jackson. And so we're saying that we think there is no difference. And we have to look to the researcher's question to figure out what they're investigating. A sports reporter suggests that professional baseball players must be on average older. Yeah, which one? Courtney put it in the chat. Yep. Professional baseball players must be older. This is where we got to be careful. If we're saying someone is older than someone else, is that greater than, less than, not equal to? Is that greater than, less than, or not equal to? Is that greater than, less than, or not equal to? It's greater than. And a way to think about this is, we'll write the alternative right here. Now remember, the first mean is baseball, right? So we'll call this mu baseball minus mu football, which is still mean 1, mean 2. Now think about this though. If baseball players are older, you would expect this difference to be what? Whatter than what? Here's a hint for the last part. If baseball players are older on average, so this would be bigger, you subtract a smaller number from it, you would expect that difference to be what? Oh, we did drink size earlier. If we did that one at the 5-minute mark. So at the start of this video, let me know if it doesn't help though. We did drink size earlier here. Greater than 0, exactly. You would expect. Now, we're not saying it is. We're just saying, well, let's see if there's evidence that this difference is greater than 0, which would indicate the first mean is larger than the second. And that does look to be this answer right here. And we are doing a what? Now, because we're doing the greater than test right here, we call this, it is still a 2-sample t, but since we're doing the greater than test, we call this a what test, which these are. This is not. Since we're doing the greater than test, we would call this a one-tailed test. So that's a one-tailed, that's a one-tailed, and the does not equals is the two-tailed. So this is not the idea of a 2-sample t. It's the idea of the sidedness of the alternative dictated by the greater than test. And do notice that when we do the greater than test, since it points to the right, you shade to the right. The less than test, which we're not doing, points to the left, so you shade to the left, and the does not equals points kind of to both sides if you do that. And good to hear, Parker. So you shade both sides. So the sidedness of the test is going to be super important because it's going to determine which way we shade the alternative. There we go, right there. So now we have to compute the test statistic. This really boils down to doing the mathematics over here. So let's go ahead and start solving out our math. So the top part of the equation, whenever we do a statistical test, is always the what. So I'm going to write here the t with complex degrees of freedom, we'll find here in a moment, is just the what. So, I mean, this is that. So the top part of a test is just going to be some sort of what for you. Like another test we do is this. That's the top part. So I'm just writing another test, not one we're using, but the top part is a difference. So if you look at this test over here and this test right here, it's just a difference. And then the bottom part of a test, that's a completely different test. We are not using this up here. We're not using that. The bottom part of the test is how we what the difference. And I know we're repeating ourselves a lot today, but I really appreciate it. It just helps remembering, okay, wait a minute. We're going to take the difference, and then we're going to put it into these kinds of units by standardizing it. So we're going to standardize the difference right here. There we go. So for the project on the one sample Z using the constant interval right to conclusion. Yeah. Brett, we've got that just in the video a little bit earlier, and we could circle back to that. But check out at the 25-minute mark in the video, we did about a 15-minute section on it. Check out the 25 to 40-minute part of the video, and I could circle back on that. I can also link you to the other videos, and we might circle back on that. And these are the similar parts. Now, these are completely different tests, but I'm just trying to show how they are the same ideas of standardizing a difference. So we're going to take our values right here. And thank you so much, everyone, for being here. We try to work as many problems as we can. And standard deviation 1. There we go. Let's start solving the problem. So when you think about your company, to answer Brett's question as I solve the math right here, your company might care about, like if I'm looking at diamonds, which I was looking at in my data, they might care about if 50% of our sales are with this type of diamond. So does that mean it's the majority sale? If we think about, 50% of something, is it possible that this is over half of it? So, why would the company care about that? Well, maybe we need to make sure we have this diamond in stock, or, it might be, good answer, work, Jesse. I really appreciate people checking my work, because that's where I make errors. There we go. Jesse got it. What was the difference? So 2.18. And here's the good news on this question, especially 2.46. We, once we draw this out, I think can probably get very close to the p-value. The reason is this p-value is going to be a lot wider than the ones we've previously been doing. This p-value right here, because of the t, and we are doing the greater than test, is going to be a lot wider than the ones we've been previously doing. We'll show how to get the exact value. Sample size is going to determine normality. It's got about 52-ish degree, 52, 53 degrees of freedom. We'll find out the exact answer. Somewhere mid-50s degrees of freedom, between 50 to 55 degrees of freedom on that. So the more, just if you're wondering how I'm doing that, the closer these numbers are, the closer it is to n-2, which is 55. And so 55 minus 2 is 53. So it's probably about 51 degrees of freedom, because the closer their numbers are, the closer it is to n-2. You don't have to know that, because it is the complicated formula. So we don't expect you to find the degrees of freedom, but it's probably about 51 right now. So I'm going to write here a t with about 51 degrees of freedom. We'll find the exact answer in a moment. Is going to be marked right here. And just look at this visually. That t of 2.426 has a much wider... Ooh, Jackson, good answers. Jackson, another 5,000 points. Yeah, I think we just did that one, Sydney. We did it very quickly at the very end. If you look right before this video, I tagged it onto the very end of the last Core Plus Mathematics. I might do a longer solve on that. So I think Jackson, and I'm not joking, we're going to throw another 5,000 points. Jackson guessed about 0.01. That could be close enough. And we definitely know our conclusion here, Jackson. So if we get this wrong, don't worry. If we get it right, Jackson just guessed the p-value without using the applet, which is something I love to point out. So this is a close enough estimate. We are definitely going to what? And great job, Jackson. So, and Sloan already put, Sloan, I haven't thrown Sloan 5,000 points for already answering people, and we love that, Sloan, right there. Thank you, class president, Sloan, right there. So we are very clearly going to what? Pretend this p-value is correct. Remember our statements? We go back here to our worded way of saying it. My p-value of 0.01 is less than, great job, Jackson, right there, my alpha level 0.05. This means I reject the null, that the ages are the same on average for the true means. I have evidence that baseball players are on average older. So I reject the null. There is evidence for alternative. And did we do it? Jackson, you just guessed the p-value. You didn't even use the applet. When you said about 0.01, I was like thinking, yeah, that's close enough. You just guessed it. You're like, it's about 0.01. There's some numbers I know, like 2.3263, 2.5758 for z-scores. So if you're wondering how I usually take good educated, let me show how to find the exact p-value if people are wondering. But if you're wondering how I make guesses, it's because I've done so many z intervals. If you go over here to the normal, and if you were to say your, like, let's say you found out your t statistic, or your z, your z is above 2.3263. I can tell you right now that your p-value will be 1%. 2.3263. We want to go above. Oh, that's the mean. Mean of 0 and above 2.3263. 2.3263. And we could carry more decimals. Yeah. It's 1%. It's like, I don't know the remaining z, but after that, but it's 1%. If you told me your z-score was 1.645, then that's going to be 5% above, or 1.6449. And then, so there's even more decimals, but if you round this, it's 5%. We'll keep it to 5 decimals. If you told me last one right here, your z-score was 2.5758, I'd say then it's 0.5%, 0.005. And so this is how, since I know a lot of z-scores by memory, then when you said, when we saw our t statistic right there, so this is how we'd get it. We'd go over here to the student t. So if you're still solving your problem, these are the steps you have to do to solve it. You ready? First, we got to find the what for the t more exactly. This is the end of the problem right here. We kind of had some fun with it, but we're going to have to find what more exactly for this problem. We got to find the real degrees of freedom. To find the real degrees of freedom, we're going to have to take the information supplied in the problem right here, and we're going to take the sample sizes and those. So here's this. We'll put it right there, and I'll disappear. We're going to go here to find the Welch's degrees of freedom, and make sure you're using this applet right here that I've just posted in the chat. Sample size 1 is 27. Sample size 2 is 28. We're just taking the ends right there. And then standard deviation 1 is 3.58. And standard deviation 2 is 2.69 right there. Degrees of freedom are actually smaller than I thought. I thought they would be low 50s, my guesstimate of it. I thought 51. I was further off. I guess it's because the differences in the standard deviations are larger. It would be a lot closer to 55 if it looked like that. The closer the standard deviations are, the closer it is to n-2. If you have exactly the same, it is exactly n-2. 28 plus 28 is 56 minus 2. That's just theory stuff that you're not required to know, and that's why I'm taking guesses at the degrees of freedom. The degrees of freedom are not. The closer the numbers are, the closer it will be to n-2. But that's a little bit more advanced theory. But great work, Jackson, right there. But that's how I make my guesses at it. And so now we take the degrees of freedom, which dictate the shape of the t, and we bring it back over here to find p-value using t. So now we put in the degrees of freedom. Once again, the degrees of freedom tell us the shape. You can see larger degrees of freedom, more normal. So at this point, we're kind of going towards the normal. Now we take that t statistic we found right here, and we have to remember, this is the greater than, this is the less than, this is used for confidence intervals, and this is the two-tailed test. So going above right here, we go above, and yeah, down to the, Jackson, your answer was down to this accurate right here. We didn't even get it within the margin of error. Down to, I mean, like, unless you want to carry even more decimals, it's literally basically 1% to 3 decimal places. There's the 4th decimal 3 decimals is 1%. Yeah. When you said 1%, I was like, that sounds about right to me. I was like, it's a good guess. And our drawing over here would cement that idea for us that it's probably close to 1%. And we always like to show that our drawing is going to look like what we see on the applet right there. So you want to take your drawing and see if you kind of did what the applet is showing. And if your picture looks a bit like it, then you know what you should be getting in the applet. Graphing above the T of 2.426 on a T with 46-ish degrees of freedom. Entering those extra decimals, they can sometimes make a small difference. 46.35 degrees of freedom. And so really good work right there. Jackson, I feel like you have a very strong understanding of these concepts. And I'm glad, huge thank you, because I realize sometimes I drop some additional knowledge, but those are like the really high level understandings you can have. So if you learn the more advanced things, the thing I don't want people to think is that the degrees of freedom are n-2, but I think you understand that the closer the values are, the closer the equation will come out to n-2, total n-2, not just n1 minus 2 or n2 minus 2. N1, technically, maximum degrees of freedom, max df for the 2-sample t is going to be n1 minus n2 minus 2, total sample size minus 2. Once I saw it was outside the second z-score, you had to divide. Exactly. So it couldn't be anywhere larger than what? Like, you can't, using just z-scores, you can't really give anything larger than what? You can't really, once you saw this, you knew you had to tell me something less than what? So once you knew that, you would have to say, well, theoretically, I have to give you a value less than what? Just using z-score ideas. Since it's outside a t-score of 2, but if you think of it as z-scores, then you would say, and technically 2.5, because 2.35 is the area between here and here, and then 0.15 is the area over there. So technically 2.5. Mm-hmm. So then you're like, okay, this area that Brian has to be less than 2.5. And so since it's a little bit more over than you would think, you were like, well, since it's got to be less than 2.5, well, then maybe that's about 1% or so. Like maybe that's about 1%. Just the way I've drawn it. It looks a little bit bigger than 1%, but you're like, maybe it's about 1%. And you were right. It was basically 1%. Now we are using the Z method. Remember, the bigger the degrees of freedom, the more close the Z and the T converge to the same ideas. So yeah, that is a much better understanding of this than just plugging things into the applet, usually why we do the drawings. And it all relates to chapter 5, which I know is a tougher chapter, but I'm really proud when people really understand it. There was a few more. Jesse, we did your question right there. What was the other questions we had? Trying to do as many new questions as we can do. Let me see what other ones people had. We've done the homework. What other ones do we have? Which questions have we not done? We did the sugar one during class. We might do the sugar one again. Yeah, Sydney, let's do the sugar one. We did it during class, and so we haven't done it during in office hours people can see. And the reason I want to do the sugar one is it uses jump output. You have to know how to read and look at jump output. So that's a really good one right there. Yep. That's great. Let's do the jump output one. I think that's a really good one for us to do right here. It's a very short question, but you know what we're going to do right here. We're going to turn it into a larger question and talk about what you need to know, especially for the test. So here we are, Step 1, Chapter 17, quiz. Sugar content. The data below shows the sugar. Okay. So with this right here, experiment was done. Oh yeah, that was a cool one. We'll do one. This is a quicker one. We'll do it here next. So what do you notice right here? All the data is what? The first thing to notice is what about this data? All the data is what? They're numbers, right? What does that mean? All the data is numbers. So what's kind of data is that? All the data is what's? Because we have to know what we're doing. It's quantitative. And then we got two groups, right? So we got adult cereal, children's cereal. Which one has on average more sugar in it, right? So we're going to compare the average amount of sugar in adult cereal by taking the mean for adults and compare the average amount of sugar in the children's cereal by taking the mean for children and see if there's a difference in the means, 2 sample T, when we compare the difference between two groups. Copy to clipboard right here. Great job. Categorical X, quantitative Y. And let's copy to clipboard. Now you're going to hit Control C or Command C, make sure it copies, and then hit Done. So this is floating around your computer's mind right now, copied, and then you want to go over to Jump. You can be anywhere inside of Jump and go to File, New, Data Table. File, New, Data Table. Now when you go to File, New, Data Table, don't click inside of it yet. Don't do it. Now, go to Edit, Paste with column names. That is super important. I'm pausing here so you can see, click this one. If you click Paste, it won't work properly. Check if you have column names right there. Jackson, that's where the 1,000 points. Exactly. If you don't have the column names and it looks like this, you paste it instead of pasting with column names. There is a quick key shortcut, Control-Shift-V right there. So you can do it with a quick shortcut, but I used to do that, and the people would say, how'd you do that? And I'd say, I pasted with column names. They say, where is that? And I say, up under Edit Paste. So I try to show everything that's easily replicatable, but there's the quick key, Control-Shift-V, to do it like super quick. Exactly. Now we have, exactly. If you don't do it properly, Jackson, great job. You will see you have, oops, there's the points. You'll see you have categorical data like that red one right there. Oh, did I give? I give 1,000. You'll see you have categorical, but you want quantitative. Now there's an issue here. I want to show the issue right now. Right now, this is not working properly. Because if you have two quantitative variables, you're actually doing what? This is a tools and techniques review question. If you have two quantitative variables, like quantitative, you'd actually be doing what when you analyze this? If you have two quantitative variables, you'd actually be doing what? This is a tools and techniques question. So the way this question would have to be worded is like, is there some sort of association between the adult version of a cereal and a children's version of a cereal? We compared, do adult cereal, like there's adult Rice Krispie treats and children's Rice Krispie treats. And we want to see if there's some sort of linear association between it, that adult cereals that have more sugar content, the children's version, which this data is not set up for this. It's not what the question is. We'd get regression. We'd get regression and correlation. Two quantitative variables, Q straight enough, no outliers, plot doesn't thicken. Two quantitative variables. No, don't do that. So here's what you want to do. Tables, stack. Tables, stack. This takes two columns or more and stacks them on top of each other. So you're just going to go table, stack, double click both. So now you're stacking these columns on top, and then we hit OK, and here's what our data looks like. Notice now we have a categorical variable, label of the cereal, and the data, which is how much sugar's in them. So now we have the categorical X we need and the quantitative Y we need. Analyze, fit Y by X. Analyze, fit Y by X. That's the theory of what we're doing, is we're comparing groups, X, and using it to explain. So we're comparing, does the label explain the data, which is the quantitative Y? So remember, 2 sample T has two groups, categorical, with a quantitative Y of interest, and here's the 2 sample T. Now we don't have the 2 sample T yet. We could go right here and go to quantiles to see the side-by-side box plots. Good for the project. Comparing X to understand the output Y, something is happening, and we can go here to the t-test to get the actual t-test we need. Now remember, side-by-side box plots, which you have in your project, are used to compare multiple groups. So we do get the side-by-side box plot up there, and then we do get the quantiles for the 5-number summary and additional quantiles. But the thing we really care about right now is the following. And we have to think about what everything here means. So this is probably one of the most important parts of this video. We've actually already done the question. But you can write your null hypothesis right here by writing mu, and then the null. And that they're equal. Or would you just put equal between them? I'll show you why. So your null hypothesis would be what? That the what for children's cereal is what the adult cereal. What is your null? You would just put the equals 0 over here and do equals 0 and read through that. If you were to subtract these means, the difference is 0, that they have no difference. Oh, no lag. I reset the internet. I'll reset the computer. I'll reset the internet. Yours keeps lagging. It might be my internet provider, which is out of my control. We did reset the internet. Maybe I'll reset it again. But if we are lagging, try setting it 5 seconds behind. Thank you for telling me that there's lag. I did reset it, hence by computer resetting and everything. Darren is just messing with that internet. Oh, no, right? So with this right here, what does the difference mean? The difference tells us what? So we did mean of children minus mean of adult. It's the way the test is set up there. So what does that mean? In our sample, we saw what? Because that's sample mean of children. We don't know what the truth is. That's what we're going to look into. We're going to try to investigate the truth. So in our sample, we saw what? How would we explain 35.516, knowing that this is the mathematics used to obtain it? Because those are sample means. Sample mean for children minus sample mean for adult, difference found of this. In the samples of cereals we took, what does that difference mean? So that's the notation of what we did. And then that's the value. Children's, the average for children's cereals had an average of this much more. Great job, Jackson, right there. And then the standard error is a metric of variation of the difference. That's kind of the technical idea of it. Like, how much variation is there in this difference? Like, you know, when we look at the variation, which is just spread of data, and that's measured by square root s sub 1 squared plus s sub 2 squared over n sub 1 over n sub 2. What would happen if we divided these numbers? You'd get a t-statistic, right? If you divide those numbers, you literally get that. You get the t-statistic. So when you divide those numbers, because remember it's y bar 1 minus y bar 2 over the standard error is equal to the t with the degrees of freedom, which are given right here. So that's the df for the t, which is already given to us. So we got the df right there. There's the df for the t. So it's given to us. We have it. And yeah, that's the t-statistic. And then you could see right here, what's really cool is if you take all of these things right here. Now be careful. The first test is the what test. The first test right there, it says probability greater than absolute value of t. So that first test is the what test. The first test is the two-tailed does not equals. The next test is the greater than, and the next test is the less than. And you can take these values and plug them in right here for alternatives to see, is there evidence, and we could write this as an alternative now. So is there evidence for the alternative that children's cereal, and this would be greater than, that the value here is greater than 0, which would be evidence that there is more sugar in children's cereal. And very clearly with the small p-value, there is evidence for the alternative. Good to see you, Carlton. So last but not least, which is what the question gets to, we just have to think about the confidence interval. So this is everything on the confidence interval right here, and we see the lower bound and the upper bound and created with 95% confidence. Know how to interpret this? I am 95% confident that the true difference between children's and adult cereals on the mean sugar content is contained in the interval 31.22 grams to 39.80 grams, where we have evidence that children's cereal has more sugar than adults because the interval is positive. And you would definitely reject the null. And we could say that with my p-value of 0.001 or less than 0.001, I reject the null at the 0.05 level of significance and conclude there is significant evidence that children's cereal has more sugar than adult cereal on average. I reject the null that they have no difference. So knowing how to say these things, we show the wording here a lot of times, like with my p-value of less than 0.001, my is less than alpha 0.05. This means I reject the null that the difference is equal to 0 between the mean sugar of adults and the mean sugar of children. I have evidence that the children's cereal has more sugar than adult cereal. Good practice right there, and that's the full output. So if you are reviewing, make sure you know what every value here means, that I've kind of color-coded it all, just to be very clear. This T is the T ratio. It calls it a ratio because it's the ratio of the difference divided by the standard error, which is how we do test statistics. That is not the t used to make a confidence roll. The t for this confidence roll would probably be close to about 2. Why would the t for this confidence roll be close to 2? Because it's a what? So the t used to make the interval, which is a totally different t, and this is my last question, then we'll answer the... So if we made a confidence roll, y bar 1 minus y bar 2, and then you did plus or minus the t star with degrees of freedom, you'd have the same degrees of freedom, and then the standard error right here of the diff. This is not the same t. This t right here is not that t. So why would the t be close to 2? It's t star, right? Do you know what we can actually do? We could actually figure it out, because think about this. What do we know right now? You could actually figure this out. Do you know the standard error of the difference? You do. This quantity right here is the what currently? This is almost the whole chapter, basically. This question we've done right here with the output, this quantity I've circled is actually the what? That quantity I've circled is the what? Just highlighting that is the difference still. That's the margin of error, right? So we know what the margin of error is. It's half the length of the interval. So let's find the margin of error. Let's take 39.8078, the upper, subtract the lower, and the margin of error is half the length of the interval. It's 4.29. We'll call it 4.3 just for fun. 4.3 is equal to the t star, and then times the standard error. So the standard error is 2.1288. And then all we have to do is divide. And we find the t. The t used, we said it'd be close to 2. So divide by 2.1288. And there it is. And why did I think I was close to 2? Because the interval, great job, Jackson, right there. And then why did I think, yeah, it's probably close to 2. Degrees of freedom are kind of largest. And I knew it'd be kind of close to 2 because why? That's the answer right there. I had a feeling it'd be close to 2 because we're making a what? 68, 95, 99.7. Because we're making a 95% confidence roll, right? And so Z's and T's kind of converge towards the same numbers. And I also know one last fact that, and I've done a lot of these problems, if you can't tell. If we were to go here and we were to make a 95% confidence roll with 60 degrees of freedom, I think at 60, that's when it's exactly 2. So if you go higher, it's going to go below 2, or wait a minute. Oh, I went, yeah, whoops. It's not exactly 2, but I think that's the closest one, yeah. 60 degrees of freedom is the closest. Then it'll approach 1.96 as you go down. But yeah, it looks pretty normal, so it's basically 2-ish. And so that's why a lot of times when I'm estimating things, might end with this question here, but the application I use of this is pretty interesting because watch this. When I make a linear model right here, let me pull up survey 10 because that's the easiest one to use. Watch this, which I showed this in 320. They're like, what? Okay, so I'm going to make a linear model here predicting height from weight. And okay, so let me show you the summary of this model. And here is the coefficient of the intercept. So do you see the standard error right here? And it'll never be correct. Jackson, perfect answer. It'll never be less than the z. The standard error there is basically 0.6. So think, if the t is basically 2 a lot of times, what is the margin of error? So if the t is usually about 2-ish, then and it's a little bit bigger than 2. So the margin of error, since that's about 0.6 and the t is usually about 2, the margin of error on that estimate will be what? So remember, that's 0.6 and the t is usually 2. So we're just doing the same sort of idea we did over here where, yeah, exactly, 0.12, exactly. So watch this. Let's take this, or let's just do 0.6. It'll be 1.2, 0.6 times 2. That's the margin of error. Let's take the estimate and do plus the margin of error minus the margin of error. Now watch this, confident. And you see those numbers we just calculated? 55.14, basically the lower. 57.5, basically the upper. So we just basically did a 95% confidence interval by hand, which this is also creating for me right here, which that's why, oops, what's it doing? Don't you do that. So a lot of the work is done for us in statistics. We just have to understand what we're doing. And then I knew kind of what I would be getting, that the standard error is the estimate of uncertainty. And then the estimate is the center of the interval. So I know what I'm doing here when I say, okay, this is the center plus or minus the uncertainty times 2, because standard error is just a metric of variation or uncertainty in your data. And if you take 320, I will just constantly call this uncertainty. Like that's our uncertainty in what we're estimating. And you can just be like, oh, well, this is my uncertainty of the difference. I should probably say that into a 1 too. So that metric right there is your uncertainty of the difference. Yeah, that's what I like to see. That's why I mentioned these things. That's just like, you're like, I think the difference is this, but I don't know. Maybe I'm off by about this amount. So the standard error is just a metric of like, I don't know. I mean, maybe it has this much variation in it. So I don't know. I could be off by about this amount. You want smaller standard errors because then it leads to more significant tests, i.e., if the standard error is smaller, the t ratio will be bigger. If the t ratio is bigger, you land further over on the curve. Further over on the curve leads to smaller p-values. So you don't want a lot of uncertainty. That's what standard error is. It's uncertainty. If you have a lot of uncertainty, then you're probably not going to find results because you're like, well, I don't know. I mean, it could be, there's a lot of variation in this data. I just like the conceptual ideas of these. Like, what are we doing and why? Any other last questions right here to finish off? Really good office hours today. Just working on everything. Yeah, so excellent work. The data below, we did a whole bunch here. Sports reporter, data, core plus mathematics. But the sugar example is probably one of the best because it shows you jump output. I say, I am whatever, could be anything. Oh, well, that's the problem, is if you go and do T statistics, like if you go, can we change the confidence level on this? Where's confidence? Set alpha level. Other. If you set the alpha level to something like this, ridiculous, then, confidence 1, jump. No. That's not a confidence of 1. Confidence of 1 would be anything, and that is a great way of putting it. So I don't know if jump's actually calculating that correctly. Yeah, now it's mad at me. Now it's saying it can't do it, which it should say, because it would just be, did we do, yeah, let's do that one to end here, Jesse. Thank you so much. Let's do supposing experiment to end right here. I think it's a shorter one. Oh, we got to put in the numbers. Well, now we got to put our alpha back. Here, we'll go grab those numbers. We forgot to solve the problem. We just put in the lower bound and the upper bound. That's what we do. There's the lower bound. There's the upper bound. Let me disappear. The confidence is 31.23. And then 39.81. Don't change your alpha levels or else you'll not get the right answers. And then adult serial average between lower bound. More notes, children. Lower boundary of 31.23. And upper boundary of 39.81. That should do it. I just realized, I was like, wait, we haven't done this. Good to see you, Andrea. Yay! Okay, let's go check out that popcorn kernel one, right? And I think, is it one that asks about, can we use the methods, is it? Yep. Ask the margin of error. Mm-hmm. Is it this one right here? We'll finish with that one too, Nicolette. Thank you for asking, Nicolette. Is it this one, Jesse? Or is it the other one? Is it this one? This one wants that one. Mm-hmm. Okay, what is the appropriate alternative? So when we do the alternative, we have to look to the researcher's question. So it says, suppose an experiment was done to gather data on the number of unpopped popcorn kernels in a microwave popcorn. Half of the students took home one bag, put it in the freezer, half left it on the counter. Each group counted which of the following is appropriate test to see whether the freezer method left fewer. So if the freezer method left fewer, we would see that the mean for freezer is wider than the mean for counter. So if the freezer method left fewer, and they might change the wording on this, so make sure yours follows it. If the freezer method left fewer, then we're looking for evidence that the true mean for freezer is what the mean for counter. If the freezer method left fewer popcorn kernels, great job, Jackson, right there. We'd be looking for evidence right there. Boom, good stuff right there. And we'll finish off with the core plus mathematics, and the null would be equal, right? Good work. And so now, core plus mathematics, confidence interval 1. Step 201, chapter 17 wheels. So with the core plus mathematics confidence interval 1, I have to delete out our answers here. We can talk about how we did it. The margin of error is always what the length of the interval. The margin of error is always what the length of the interval. The margin of error is always what the length of the interval. This is a good thing to memorize. The margin of error is always half the length. Great job, Jesse, right there. We've been throwing some points lately. So margin of error is always half the length of the interval. So if this were to say, great job, upper minus lower divided by 2. Yep. And think about it visually. It's like, I always like to do an example like this and try to write these own examples for yourself, your own examples, where we say something like, your friend says, let's go get a really nice steak dinner. It's going to be between $60 to $80. This is going to be an expensive steak dinner. So when your friend tells you the steak dinner is going to be between $60 to $80, what's their margin of error? What is their margin of error? The margin of error they have, they say, man, we're going to get a really nice, best steak dinner you've ever had. And you're like, I don't got that much. Plus or minus 10, right? And so the margin of error is half the length of the interval. The length of the interval here is 20, upper minus lower divided by 2. Well, we'll do divide by 2. And then the margin of error here is 10, because if you go to the center of the interval and go from 70 and go plus 10, minus 10, and 70 is said to be the estimate plus or minus the margin of error. So 70 plus or minus 10. So you can figure out the estimate of this interval by finding the center. The center is upper plus lower divided by 2. You're just averaging the numbers. Once again, writing down the formula is one thing, but then understanding conceptually is another. So try to do examples like this. Try to repeat them to be like, well, if my friend says a steak dinner is going to be between $30 to $80, what would be the margin of error? Okay, $30 to $80 is an interval of 50. So 80 minus 30 is 50. And 50 divided by 2 is 25. And the center of the interval will be 55. I'm just changing the numbers on you here. So try working different numbers. Exactly, Jackson. At that point, you understand how to get the margin of error for any sort of questions. And there are other instances where we could do stuff like this, where we could give you the upper and the middle. So how could you figure out the margin of error if you only had this information? So there are other ways of doing the questions. So I like that random quote, Carlton. If you only had the center and the upper, how could you get the margin of error? Yes, exactly. Because you realize it's half the length of the interval. So you're like, well, I could just do that. And I could just get, well, this is the margin of error right there. So that's where I've had people on the test say, well, wait a minute, I don't have the upper and the lower. And I'm like, well, what do you have? So I think visualizing it and seeing what you have and think you're trying to get half the length of the interval. The center and the upper is also a distance of a margin of error. The center and the lower is also a distance on a margin of error. That is a U, because my handwriting is bad. My gosh, my handwriting is bad. How I saw you mention how E could do it. Yeah, exactly. Yeah, thank you so much. Check out those older videos. There's so many things. There's so many neat ways to solve stuff. But that's all we did right there. Upper minus lower divided by 2. And then with your hands right here, when you go from a 95 to a 99, you're changing either the Z or the T. And the Z or the T is getting water when you, with your hands, say 68, 95, 99.7. Your interval is getting water with your hands as you do this. So you just have to think, if you made a 99, because we made a 95 to begin with, your interval is getting bigger. And what's controlling the interval, as we talked about in previous questions, is going to be the T statistic right here, or the Z, depending if we do a T or Z interval. So the star on these intervals denotes the percent confidence, and a T of basically 2 for most instances is about 95% confident. It depends on the degrees of freedom, but most of the time for decent sample size is a T of 2. Once again, computer software, or we can look it up to get the exact T's. So it's going to definitely be a larger T for certain. So the T is going to increase, which is what they're talking about here with the critical value used to make the interval. The last thing right here is we're not talking about an individual student. This is an estimate of the true difference between them. So it's not a singular student might do better. It's on average. Now, why is it that the core plus mathematics will do better? Because if the core plus mathematics does better, this interval will contain what numbers? So since this is first mean minus second mean, notice how it's the first mean, mean 1 minus mean 2. So if the first mean is the higher mean, the interval will be positive. Because if we have something like 10 minus 6, that would make a center of 4. I guess it's actually closer to 10 minus the center of the interval is about 8. So it'd have to be something like that. So that would be about the center of the interval of 8. I'm just kind of guesstimating it. I know it's not exactly 8. But if there was an average of 10 for the first mean, an average of 2 for the second mean, when we compare the sample means, then we would see 8 at the center plus or minus some sort of margin of error like 3. So that'll give you 5 to 11. So with this, we have evidence that the first mean is higher. And remember, the first mean is with the positive, the second mean is with the negative. So positive interval, first mean is evidence of higher than the second mean. And the last but not least, is this evidence of a difference? Well, no difference would include what in the interval, which it's kind of alluding to down there. If there is no difference, then we should see what in the interval. If there's really no difference, we should see 0. So this interval suggests evidence of a difference. Like if I told you you'll make somewhere between negative $1,000 to $3,000 more working this new job, you're thinking, wait a minute, this new job might cause me to what money? On this new job, you'll make somewhere between negative $1,000 to $3,000 more. You're thinking this new job might actually be a what of money for me. You'll make between negative $1,000 to $3,000 more. You might lose money, or it might just be no difference, right? Because zero's in the interval. There might be no difference between your new job and your old job. But if I say you're going to make between $10,000 to $15,000 more working this job, and I've got 99% confidence, free labor right there. Well, we were talking about the differences and the difference between one mean two. We're talking, and so if we said between $10,000 to $15,000 more, that would be evidence of a difference because zero is not contained in the interval. So always try to relate it to how people talk, and I think that can help with understanding. We think that the core plus mathematics approach has a difference that is about 6 to 12 points. I'm rounding very harshly on these, or 5 to 12, somewhere in that interval. And that's a good question. It's a lot of interpretation to understand what the interval means. But with that, I'll put on the old outro we do a lot of times right here. A little quick outro. We'll be back here soon, about 30 minutes for class. Show up. We got some chi-squared. Until then, bye for now, everyone. Bye!